today's eeNews interview. I'm meeting up with Josep Montanyà in Silvestre, and he is the founder and CEO of Nanusens. And Nanosens is making nanosensors, basically MEMS, microelectromechanical systems. I need to practice on that, I think, more. Good morning, Josep. But we are talking about nanosensors and MEMS. Now, I think in the world of MEMS, there are lots of companies doing MEMS. You know, I think all over the place you have them, and they produce these really nice sensors, which help us, you know, to communicate with the analog world and the digital world. They're in all our phones. But at some point in time, you were also in the MEMS business and said, okay, we can enhance this. We can do this better. What was that? What made you, convinced I can do that better?
So, yeah, good morning, Wissam, and thanks for the time of this interview. Yeah, so basically I set up a company called Biolab Microsystems back in 2003. It was like part of my PhD thesis, if you want, and I set up the company with the goal of developing a low voltage actuated RF switch, because one of my professors at the university told me that would have an even market appeal. So after 2 years of developing that, I went on a trip to the US to show that to a number of semiconductor companies there. And then is when I had a shock with the reality, and I saw that the industry was not looking for that device. So
that's how you put in all the effort.
Yeah. And the investors that I had money, etc. But then I started learning what the industry was really looking for, and the industry was looking for lower cost, integration, and making MEMS as close as possible to the standard in solid state manufacturing, which is CMOS. Yeah. So that was 2005, and then is when I started changing the purpose of that company and starting my research in how to make MEMS in CMOS, because that is what the industry was looking for, and today is still looking for that.
Yeah. Today is still looking for that. So I understand, but what is the industry looking for then? You know, we have MEMS, they work, they're in all our phones and computers and systems all over the place. What exactly are they looking for to enhance, and perhaps what you are working on now?
Yes, so the customer requirements for MEMS ICs are very clear, and it's very similar to all the ICs. So they want lower cost. So they want price erosion every year. They want smaller size. They want lower current consumption, and they want to have them in very large volumes. So because and all this is very difficult to fulfill these 4 requirements by existing MEMS companies, and the reason is because there is there's no manufacturing standard for MEMS. Unlike with solid state chips where you have CMOS, no? Yeah. So the economy of scale is limited, and then that's why you cannot reduce cost. You use legacy equipment, not state-of-the-art equipment, so it's difficult to reduce size, to reduce performance and power consumption, and then many times a shortage of supply. There are so many applications that are being developed in terms of AIoT, wearables, in addition to smartphones, but the market cannot provide that. That's why one requirement also is to be able to produce them in very large volumes.
Yeah. But from my, I must say, limited understanding of how MEMS are produced, it is comparable on how we produce our semiconductors in many ways. I understand, but your production is different. I feel. I understand that. We have now the mechanical part, let's call it this way, and we have the electronics parts, two different worlds that need to interact with each other. And from what I feel, what I understand, but correct me if I'm wrong, is that you, with your research and your development, are looking to integrate these two to bring the hardware, the moving part, closer to the electronics part. Is that right?
Yes, that's correct. So if you open the package of a chip, of a MEMS chip, so inside you will find that always you have at least two dies that come from two different wafers. One is the electronic part, as you say. The other is the mechanical part, the MEMS.
Yeah.
So for the electronic part, this comes always from a CMOS wafer. No? And then the mechanical part, it's a MEMS wafer that is produced in a bespoke manufacturing process, which is property of the MEMS company. So you always need these two parts, but the mechanical part is produced. I mean, there's not a large economy of scale there, no? Because it's proprietary of each. So what we are doing at Nanosens is that we use CMOS to make both the electronic part and the mechanical part.
From one wafer?
Exactly, from one wafer, yes, yes. And you're also right in that at the end, for the mechanical part, it's also semiconductor technology, so it's photolithographic techniques, micromachining. So it's very similar techniques than what you use with the CMOS, no? But it's different materials, but the sequence of steps is different. Here it's more a logistic thing, if you want, no? So it's not. So for solid state you have CMOS. There are huge foundries, and everybody uses a fabless model, no? So there's a very large economy of scale. For MEMS, this does not happen. It's essentially that.
Yeah. Now, one of the things, because I've been trying to do some research on your website, etc. Now, one of the key factors of the success in your research is a new way of etching, which basically means that the metal layer part can be etched in a different way. I think that was also one of the enablers of just looking to see if you can have the MEMS and the electronics from one wafer. Is that correct?
Yes. So what happens is that if you want to have MEMS inside the CMOS wafer, MEMS, it means mechanical movement, no? Something that needs to move. So inside the CMOS wafer, like in the solid state process, you cannot have any movement, because to have a movement you need some empty space to enable that movement. So if you want to have a MEMS in a CMOS wafer, you always need some type of post-processing. What other companies that have tried to make MEMS in CMOS have been doing is adding more materials and more layers on top of the CMOS, either by wafer bonding or by micromachining on top of the finished CMOS wafer. Our approach is radically different, and as you say, what we do is that we etch away a little bit of material to create that empty space. So in particular, what we'll remove is silicon oxide in what's called the back end of the CMOS. So if you make a cut on the CMOS, at the bottom part you have what is called the front end with the active part and the transistors. Above that, you have it's like a small PCB, no, with metal layers which are separated by silicon oxide to make the electrical connection. So what we do is that we place the wafer into machine with hydrofluoric acid in vapor stage, and the vapor chef etches away the silicon oxide of the back end of the CMOS chip, and it leaves the metal layers. So it's very selective. So this means that the metal layers then are free to move. So we make our MEMS devices using the metal layers that are already there in the CMOS, which were intended to make electrical connections, but we use them for different purpose on part of the chip, which is a mechanical movement. And then we have also the other part with the electrical connection, so we have both.
So that of course I realize that is a lot of research, and of course then there is always the reality check. In what sort of applications can we find your nanosensors? Because you actually bringing the MEMS to the nano level, NEMS with an N. How far is the research? How's the reality? Are your nanosensors already in applications?
Yeah, and it's true that actually it's nanosensors, because one of the benefits we have of using CMOS, among others, is that we have very small. We can use very small feature sizes. No, in a 180 nanometer node, we can use down to 300 nanometers.
Okay.
When typically for MEMS, it's in the order of microns, the resolutions that you have there.
Yeah.
So the first two devices that we have developed and that we have tested extensively in the lab with all the reliability tests, it's an accelerometer, so a 3D accelerometer.
Yeah.
This is in the area of sensors, and we are very advanced in the pressure sensor. And then we have another line, which is a radio frequency tunable processor. Here we have developed a capacitive switch, and in particular a digital tunable capacitor, which is for applications like antenna tuner, no, and in order to increase the antenna efficiency in smartphones above. For the higher frequencies of the 5G, so above, beyond 2 GHz, we can increase antenna efficiency beyond 30%, which is very relevant, no? Because it extends battery life and range. So these are the first two applications. Beyond that, we are working on other sensors like gyroscope, magnetometer, microphone, ultrasound, infrared. It's not that. And that's actually one of the nice things about this technology, because typically a MEMS process is developed to manufacture a specific type of device. No? That's why most MEMS companies specialize, no, in specific types of products. With this technology, we can actually build many different types of products. It's not that we can build everything.
It's a very versatile technology. It can be used in many applications. I see.
When it comes to optical, biocompatible materials, we have the limit there. And that's because the usual approach in MEMS is that you design your MEMS device, and then you design your manufacturing process, no? Whatever materials you need, whatever, etc. We've done it the other way around. So we started with the process, said it has to be CMOS plus vapor HF, and then we figured out how to make the design to make it work with this. And actually it's taken many years and many silicon runs and wafers destroyed to get to the point where we are now. Because these things you can simulate to some extent, but at the end you can try.
You have to try. That was basically one of my next questions. What is the biggest challenge to overcome in your whole process now to actually to get more acceptation and nanosensors? Are you IPing this technology out to other companies, or what is your longer term vision on this?
Yeah, we think long term we will become an IP company, because at the end of the day, what we are saying is that you can have MEMS devices in standard CMOS, so that at the end it's an IP block. At the beginning of PCBs and ICs, you had different packages for each of the electrical functions, and operation amplifier could be a separate block. No, now most of that has gone into the ASIC, but you still have the sensors that need to be different blocks. What we are saying is that can be integrated into the digital processor, so as to reduce that. However, in order to get there, we understand that first we will be selling products, no? So we'll sell products. But although that was our plan, we have already signed a license that's valid with Azotec, and we are having discussions with another two IP licenses that hopefully we'll be able to announce soon.
So thank you very much for your time and your explanation.
It's been a pleasure. Thank you very much.